All right, buffers are things that you actually have more experience than you think you do. So on the top of your note sheet, it has the basic definition of it. It's a buffered solution resists pH change when H plus, or we'd say acid, or OH minus, which is base, is added. So when we add an acid or a base, our solution really doesn't change in pH. Then you know you're dealing with a buffer. So we have to figure out, how do we get to that point? How do we get to what qualifies as a buffer? So I have two different problems here on the top. First one's acetic acid. Please be mindful, sometimes we write it a little differently, and we would write it like this, where we would shortcut the acetate ion and just call it AC. So then we could write it like this as a shortcut. That's just simply a shortcut. All right, so I have the equation below here, and I'm just asking for the pH. So we've done this many, many, many times. So I have 0.5 molar of a compound, or of a solution, right? So I'd have my solution's going to move to the right. I'm going to consume my product, and I would get something that looks like this, right? I put it into the equilibrium expression. Right, there's my equation. I cross out x. I'm hoping I can assume that. I'm going to have my x equaling my H plus concentration, which will help me get to my pH. I apologize for my rounding here. But ultimately, when I plug this all in, because this will go into there, I'm going to get a pH of roughly 2.52. Okay, so that's negative log of that. And I'm going kind of fast because these are things that we've done. But now, what if I add a salt? And the salt has a common ion in it. And what I mean by that is, when you look at this salt, like all salts that are soluble, and I know this is soluble because it has an alkali metal in it, it's going to break apart into its ions. So I have Na plus and C2H3O2 minus. And each of those carry, if this was 0.5 molar, now this is also 0.5 molar, and so is this. So I have 0.5 molar. All right, so sorry, this should have a little minus on there. So now when I come back to this, we're adding this. So this is really important. So this links. This is the same problem. So I have, or I had, 0.5 molar of my weak acid, and now I'm also adding from this 0.5 molar of my ion. Okay, they're both in solution. So we have to assume some things. So there's my 0. So now I would have something like this. Okay, I would again plug this into my equilibrium expression, though it's going to look very differently than before because of the fact that I have more things going on. Okay, so we have actually entered this world before, and what is it? It's when these two expressions are exactly the same, right? We could cross off those x's, and then those 0.5s are going to cross off as well. So what is happening, if you look at these, is I have, this is an acid, and this is its conjugate base. I have equal amounts. And when you have equal amounts, that's going to make a really great buffer. So now if I plug all this in, again, I would take, well, x equals 1.8 times 10 negative fifth, so I take pH equals negative log of that. Now my pH is 4.74. Part of the reasons for that is that because I have an ion on the other side, it's kind of stopping the dissociation from going across as far. It's not going to make as much H plus because I already have some of that C2H3O2 on the right side. Okay, I have not shown you what a buffer is yet. I'm going to show you, well, I have, but I'm going to show you the effect of it. So this is the key part, is that I have this, okay? So let's take that solution now. And I'm going to take some base, and I'm going to add it to that, okay? So now this is where you can start seeing the effect. So it says determine the pH if 0.01 moles of NaOH is added to 1 liter. That's really big. When it's 1 liter, that means the molarity and moles are basically the same thing. To the solution above. And when I say above, I mean this one, okay? So let's fill in the things that we have. And this is going to be really key here. So I have 0.5, and I'm going to write moles over liters just so you understand that it still works out right now for me. And then this is my strong base, and that's going to come from my OH. So I was told that I had 0.01. And because it's in 1 liter, I can do that. Otherwise, I have to consume moles instead. This is water, and then I also had 0.5 over here before from above. Okay, so now what's going to happen? Well, because this is a strong base, this is going to drive it to the right. This is going to drive it. So when an acid and a base react, they always are going to make water. So when an acid and a base react, it's always going to produce water. Okay, so my acid or my base has to be completely consumed. So you just look at them, and I have less base than acid. So what's going to happen is my X is going to actually be the amount that's going to be consumed. And then I add or subtract. So when I'm all said and done, then I have an amount that looks like this. Right? So the fact that this is 0, that's a good thing. It means that it consumed H plus until it ran out. Okay? So now, what do I have left? Well, here's the first thing, is that if you look at your products, I don't have H plus or OH minus. I can't do a pH problem without H plus or OH minus. So what confuses a lot of people, and we can do this in 2 different ways, so I'm going to show you how to do it in 2 different ways, is that the acid now must redissociate. It has to basically refine equilibrium. It was forced. It was forced to the right. It doesn't mean that that's where it is going to naturally end up. Okay, so now if you look at my final equation, my acid is sitting there, and I initially have 0.49 from before. I, at this exact moment, have 0.51, and I don't have any H plus because it was all consumed, if there were any. So now, like everything else, we just move forward. And then I plug this into my equilibrium expression. Right, my X is going to equal my H plus. Again, I'm shortening this up a little bit. You can get that calculation. But then when I'm finally done, my pH is 4.76. What happened? My pH was 4.74. Now it's 4.76. It went up. It became more basic or less acidic, but not by much. I added OH, and it only went up a little bit. So that would show me that that is resisting pH change. All right, well, there is a different way to do this. It's called the Henderson-Hasselbalch equation, and you might really like this. So let me just show you and break it down once. If I show you Ka and a generic acid that we all know and we've seen, right? And it would be that, right? Let me just, stems from that. Well, if I rearrange this just a little bit, and I say H plus equals Ka times my HA over my A minus, well, now I can do some things with this. So if I look at that, what if I take the P of everything, so the negative log of everything? So if negative log of H plus, that becomes pH. Right? Negative log of Ka becomes pKa. And because I'm multiplying that with log, it becomes an addition. So this becomes log of. It ends up flipping. You don't need to know that, but it does. And then I end up with that relationship. So this basically would then say that my base is on top, my acid is on the bottom. There is another one that you could do. If it's POH, I'll do this kind of smaller. It would be PKB plus log of, and then I have my acid on the top, and I'd have my base on the bottom. And the whole point of what I always like to think of, whatever's on the bottom, it's like the foundation of that problem relates to what you're solving. So pH deals with acid, and pOH deals with base. So now, if I plug that in to that equation, I can say pH equals negative log of my Ka plus my base, which was 0.51 to begin with. Like, this is before I even dissociated, over 0.49. And what's cool about this is I didn't even have to do as much work. And I get that. Versus beforehand, so I have a change of pH of 0.02 because beforehand it was 4.74, right? So that is what a buffer calculation deals with. I understand that this is new and slightly different. It's going to be kind of confusing, but we'll continue to work on it as we go. So we'll be great. If you have any questions, obviously you